Okay, welcome to our last major unit, electricity and electric circuits. So electricity can take on a couple different designations if you want to think of it that way. So the one you may be most familiar with is static electricity. You probably have done that in grade 9 or 10 somewhere along the lines. And if you shuffle your feet across a carpet and then touch someone, or you rub a balloon against your head, those are examples of static electricity. So we have a movement of charged particles, but it isn't a continuous movement. They sort of move, they charge up an article or an object for a while, and then over time they either return to their neutral state or they discharge, but it isn't a continuous flow. And then dynamic electricity is where we have a continuous flow, and it could come from a battery, it could come from a generator, it could come from the plug in the wall. There's a continuous access to what we're going to eventually look at is the movement of electrons. So that's a continuous flow. Okay, so that's dynamic electricity. And then you have a third group, which is sort of a very specific group. It's lightning, and it's a little bit of both. It has some static, and then it has dynamic. And if we get a chance, we'll talk a little bit about that as well. Okay, so static electricity, transfer of one charge from one object to another. So the excess charge can sometimes be seen. You can either see that as hair standing on end here, that's one option. If you take a balloon and rub it on your head and bring it close to some water, it'll bend the water away, since water is by a dipole and it has a positive and negative side. Okay, and then sometimes you can even see the discharge. Sometimes you can see that shock zap or jump from your finger if you're shuffling across the carpet. So normally I'll try and fit some demos in here if there's time, but I've got a picture here just in case. So there are two types of charge, and again, these are human conventions. There's nothing in nature that says they're positive or negatives. They're just conventions that we have used because they work mathematically and they work for our understanding. Okay, so there are two types of charge. There's positive and negative charge. An object can be neutral, and therefore it's not affected by either type of charge. But positives and negatives affect each other. So positives would repel each other. Two negatives would repel each other. But a positive and a negative would attract each other. So that whole idea of opposites attract, that's where it comes from. So dynamic electricity is the movement of charged particles, usually electrons. For all of our discussions, it'll be electrons, through a material called a conductor. So a conductor has an internal lattice structure that makes it easier for electrons to escape the hold of the nucleus on them. So if you think of all your protons and neutrons, all those nucleuses are sort of locked in place, and then the electrons zip around them and they jump between different nucleuses, or nuclei, sorry. Metals are good conductors of electricity. Let me just shimmy my picture over here. Okay, so if you look at this picture, and I'm going to warn you, these pictures are simplified models so that we can look at them. When you talk about electrons moving down a wire or a rod or conducting, there are zillions of them, as we'll see when we get to the current section. So this is just a simplified model. You can't go in here and count the electrons and get an idea. There's just way too many. Okay, so these little arrows on here are vectors. They're showing the direction, and you'll see electrons, they're sort of moving to the right, but some of them are moving down, some of them are a little chaotic, and they tend to bounce all around. These positive ions, that's what forms the lattice, so these things are all locked in place. And an insulator would be the opposite of a conductor. An insulator is something that holds on to its electrons very strongly, and it doesn't let them move around. So the movement of the electrons is what we refer to as electricity, and there's a little chart here if you want to take a look at it, if you can see it. So examples of conductors: copper, aluminum, brass, graphite, all metals. Electrical insulators, plastics, rubber, dry wood, glass, ceramics. And if you think of some of the things around your house where electricity is used, specifically lights, you'll notice that there's normally some sort of conductor surrounded by some sort of insulator. Okay, so if you get a chance, go look around your house, see what you have. Okay, we'll do a quick discussion on fields. We do more of this in grade 12, but just so we understand what a field is, you've already been working with it. So a field is a way of describing an interaction at a distance. Okay, so that's a really big idea. So interaction at a distance, notice it doesn't say force, it just says an interaction. An interaction at a distance means something doesn't have to touch. Okay, so you are most familiar with the gravitational field, probably. At least that's the one you're most aware of. So the gravitational field on Earth extends to all objects with mass, but the effects of the gravitational field do not require direct contact. So like a car collision, there would be two cars hitting, that's obviously contact, but the gravitational field is affecting everything whether you're touching it or not. Okay, and it is only attractive, and that's really important. If you've ever had a chance to play with a magnet, we do have magnetic fields, okay, and they extend from one pole, the north, to the other pole, to the south. Okay, and again, they can interact with objects without touching, and again, they can be, though, attractive or repulsive. So they have two options. Okay, and lastly, and this is the one that it's everywhere in your life, you just may not be aware of it, an electric field. So an electric field surrounds all charged particles. It can also extend from a group of charged particles, and it can be attractive or repulsive. Okay, so when we talk about fields, we can show them with vectors and things. So if we look at this field here, you can see got a couple of vectors representing the gravitational field, and you'll notice they're all pulling down towards the Earth. And that would just extend off into space. The farther you get from Earth, the weaker those would get. But again, we'll talk about that in grade 12 a bit more. When we have a magnet, better use a different color here, let's use blue. You would have fields that flow like this, from north to south. Okay, they might even go all the way around. Okay, so and within that field, your compass and those types of things, your compass would have a needle and it would align with those fields. Okay, and again, we'll talk a little bit more about that in grade 12. So fields are just an interaction at a distance. Okay, so now, movement of electrons in a circuit happens when an electric field is applied. So this will be new terminology, even though it's a concept you've dealt with for many, many years. The electric field, like a gravitational field, can make charges move. Okay, so our most familiar tool for doing this is a battery. So when you attach a battery, okay, to a wire, like you can see over here on this right-hand diagram, you can see a little red line that indicates that electrons will want to start moving. Now, the original convention was positive and negative, and they had ideas that there was a buildup of excess charge or more pressure, whatever the definition or analogy they use. So they always thought that electrons flowed from positive to negative. But what we find in the future, and we'll talk more about this in current, is that electrons actually flow in the opposite direction. Say, but the field lines, and again, this is something we've drawn, it's a human convention, we draw field lines from positive to negative. Okay, so you'll see here, positive to negative, and that's what we call conventional current. We'll have more conversation with that. And then you can see inside, here's that lattice structure, and here's all the little electrons moving to the left. And we'll discuss things like drift velocity and those types of ideas. Again, if you look at this, this is a very simplified version of what you're going to see. There are literally zillions of electrons moving around. Okay, it's just a picture, keep that in mind. They do not move in little straight lines, they're not perfect, they bounce all around in a very chaotic fashion. And just so we've talked about it, a basic circuit looks something like this. You would have a battery, you'd have some things on it, a switch, a fuse, a light bulb, and then we would look at current flowing, and again we'll talk about this in our next lecture a little bit more. We would look at current flowing either this way for conventional or the opposite for electron flow. Okay, so we would have current or little electrons flowing around the circuit, and if you break the circuit like you would at the switch here, that would stop the flow of electrons. Okay, so what makes electrons flow? Well, it's this field. Okay, so this field that we apply is what makes them start to move, but we have a name for it. Okay, so the electric field applied is what gives us the push. It's not a force, though. You could think of it like a pressure if you wanted to do a water analogy. We describe the field strength in terms of its energy, though, so not force. So there's a couple of new definitions on here, and then the next slide I'll kind of give you the tie together. So let's see if we could just get some of the words ironed out here. So new words. So there is a difference in potential energy between the start and end of a circuit. Okay, so it is this difference that gets electrons moving. Okay, so if you think of a straw, for example, for a straw to work, you change the pressure in your mouth to lower than atmospheric, and what happens is the fluid in your drink goes up the straw. So it's that difference in pressure that makes the fluid, the milkshake, the whatever you're having, move up the straw. So this is very similar, okay, to what a volt is going to do. So the unit for potential difference is called a volt, and it is measured in joules per coulomb. Now coulomb is a new unit for you. Coulomb, because electrons are so small, a coulomb is the standardized number of electrons used. Okay, so, and be prepared, this right here is what a coulomb is. It is 6.241 times 10 to the 18th electrons. So as I said before, in those little simplified diagrams, they don't represent how many electrons are there. They're just a simplified version to wrap your head around what's going on. This is how many electrons can be flowing in 1 coulomb. Okay, and we're going to find that's a pretty common number. Okay, so a simplified version is a volt. Is the quantity of joules available to do work per unit of charge. Okay, so this is our energy on top. This is our Q. I'll make sure I draw a little arrow there. Q is our charge, usually measured in coulombs. Okay, so this is energy available per electron or per coulomb of charge. Okay, so that's a new topic. This is the strangest of all the topics, but it'll start to make sense when you see how it's worked in a problem. So let's have a quick look. We'll do a gravity comparison. So we have EG, our gravitational energy, mass times gravity times height. So if I have a 2 kilogram ball suspended 8 meters in the air, it has a potential energy, gravitational energy of 240 joules. Okay. If I let it fall down to 2 meters, at the 2 meter height, it has a potential energy of 60 joules. Okay. So now there is a difference in potential energy there of 180 joules. So that difference in energy, okay, that's what a potential difference is. So when we talk about charge and electrons and voltage, it's this change or this difference in energy that we're going to be sort of relating to. Now if we take this energy and we divide it by how many kilograms we're working with, we get the joules per unit kilogram. So this would be 120 joules per kilogram. Down here we would get 30 joules per kilogram, so I'm just dividing both those numbers by 2. And now my potential difference is 90 joules per kilogram. So if I change the mass of this ball, I could use this rate right here to figure out the potential difference. So if I up this to a 10 kilogram ball, I could just multiply this by 10 and I would have 900 joules of potential difference between the top height and the bottom height. So from our energy unit, what does that potential energy turn into? So if we have this 180 joules, well, it turns into kinetic energy. It's a moving object, so it goes from being suspended in the air to moving. Okay, so let's try this now with electricity or a charge. So it looks very similar. The difference now is it's not gravity. The difference now is that it's just this potential difference, okay, that's applied from the battery and the field. So if we had a potential energy here of 240 joules and a potential energy down here of 60 joules, that's a potential difference of 180. Okay, so over here, if we divide through by the number of coulombs, so instead of 2 coulombs of charge, we're just going to find the unit rate, and that gives us this term 120 joules per coulomb, which we would call 120 volts. Down here we would have 30 volts, okay, again just dividing by 2, so the potential difference would be 90 joules per coulomb or 90 volts. Okay, so this right here, if you imagine, these could be the 2 connectors on a battery. So you would have a positive lead and you'd have a negative lead, and the difference between those would be 90 volts. And what it is, it's that difference here that will encourage or make some of the electrons move from point A to point B. And again, so what does the potential energy turn into? It turns into kinetic. Okay, that's the basic idea. It takes a little while, so be patient with yourself. It's tricky, but it gets easier as you proceed. Okay, so measuring potential difference, and we'll do this in a simulation, or if we have time, maybe we'll do a little video model. You can have a voltmeter, and it measures potential over each object that's in the circuit. Okay, now the key is you have to put them in parallel, and parallel means it doesn't break the circuit, it gets connected around the circuit. So if you think here, this guy would have two possible pathways. Electrons could go this way, or they could go this way, and that idea of parallel means there's multiple pathways. So let's just try one quick question. Calculate the electric potential difference, so that's a fancy way of saying volts, between the negative and positive terminals of a battery if 500 joules of electric potential energy, please note energy and difference are different items, is transformed to move 125 coulombs of charge between the terminals. Okay, so let's just take a quick look here. So this is potential difference, that's volts. This is charge, and this is energy. So when you're reading questions, you have to really be careful. Does it say potential difference, or does it say potential energy? Be very mindful of that. So if we were to solve this question, let's get my pen going up here, we would have, come on pen, V equals 1,500 joules over 125 coulombs. And if we divide that out, that is what, 12? Better double check. I think it's 12. 12 volts. Okay, so if you want to pause it and try as the next one, you can do that right here. You can tell my son stole my calculator for double checking. Okay, a computer processor chip transforms 120 joules of energy while moving 52 coulombs of electrons. So we would do the exact same thing, 120 joules over 52 coulombs, and we would go 120 divided by 52, and we would have 2.3 volts. Okay, and that's it. From a calculation side, it's pretty straightforward. The concept is much more tricky. Don't be afraid to read a little bit more. So we did two sections today, so 11.1 and 11.3, and they're listed right here. And thanks for tuning in.